A popular software application serves billions of user requests. These requests could be for many different things, and the requests need to be routed to the correct destination, load balanced across different instances of the service, and queued for processing. Processing a request might require generating a detailed response to the user, or making a write to a database, or the creation of a file on a file system, or maybe all three of these things. As a software product grows in popularity, it will need to scale each of these different parts of infrastructure at different rates. You may not need to grow your database cluster at the same pace that you grow the number of load balancers at the front of your infrastructure. Your users might start making 70% of their requests to one specific part of your application, and you might need to scale up the services that power only that portion of the infrastructure. Today's episode is a case study of a high-volume application, a monitoring platform called Raygun. Raygun's software runs on client applications and delivers monitoring data and crash reports back to Raygun's servers. If I have a podcast player application on my iPhone that runs the Raygun software and that application crashes, Raygun takes a snapshot of the system state and reports that information along with the exception so that the developer of that podcast player application can see the full picture of what was going on in the user's device, along with the exception that triggered the application crash. Throughout the day, applications all around the world are crashing and sending requests to Raygun's servers. Even when crashes are not occurring, Raygun is receiving monitoring and health data from those applications. Raygun's infrastructure routes those different types of requests to different services, queues them up, and writes the data to multiple storage layers: Elasticsearch, a relational SQL database, and a custom file server built on top of S3. John Daniel Trask is the CEO of Raygun, and he joins the show to describe the end-to-end architecture of Raygun's request processing and storage system. We also explore the specific refactoring changes that were made to save costs at the worker layer of the architecture. This is useful memory management strategy for anyone working in a garbage-collected language. If you'd like to see diagrams that explain the architecture and other technical decisions, the show notes have a video that explains what we talk about in this show. Full disclosure, Raygun is a sponsor of Software Engineering Daily. Are you a Java developer, a full-stack engineer, a product manager, or a data analyst? If so, maybe you'd be a good fit at TransferWise. TransferWise makes it cheaper and easier to send money to other countries. It's a simple mission, but since it's about saving people their hard-earned money, it's important. TransferWise is looking for engineers to join their team. Check out transferwise.com/jobs to see their openings. We've reported on TransferWise in past episodes, and I love the company because they make international payments more efficient. Last year, TransferWise's VP of Engineering, Harsh Sinha, came on Software Engineering Daily to discuss how TransferWise works, and it was a fascinating discussion. Every month, customers send about $1 billion in 45 currencies to 64 countries on TransferWise. And along the way, there are many engineering challenges. So there's plenty of opportunity for engineers to make their mark. TransferWise is built by self-sufficient, autonomous teams, and each team picks the problems that they want to solve. There's no micromanagement, no one telling you what to do. You can find an autonomous, challenging, rewarding job by going to transferwise.com/jobs. TransferWise has several open roles in engineering and has offices in London, New York, Tampa, Tallinn, Cherkasy, Budapest, and Singapore, among other places. Find out more at transferwise.com/jobs. Thanks to TransferWise for being a new sponsor of Software Engineering Daily, and you can check it out by going to transferwise.com/jobs. John Daniel Trask is the CEO of Raygun. John Daniel, welcome to Software Engineering Daily.
Thank you very much for having me, Jeff.
Yeah, it's great to have you. You work on a crash monitoring system that handles a high volume of exceptions. So the way it works is whenever a user's application crashes, and they're running your crash monitoring software, the exception that caused the crash needs to get recorded and indexed on your servers so that the developers of whatever application crashed can understand what is causing the crashes. So if I'm a developer and I'm building an app that plays podcast episodes, and one of the users is listening to a podcast, and then the app suddenly crashes, I would like to know about that as the developer of the podcast app so that I can fix the bug. And in order to know about the crash, I need it to be detected and reported, and that's what your software Raygun does. And since a lot of crashes are going on across the world at any given time, your infrastructure is constantly getting hit with requests. Can you describe the requirements for what you have to do with each of those crash reporting requests?
Yeah, absolutely. And I'll just fill in a couple of extra bits there too.
Please, yeah.
Raygun does work with about 25 different programming languages and platforms. So mobile devices, so through to desktop, back-end services, front-end JavaScript. And we also have what's called real user monitoring. And that's tracking the performance story as well as high-level analytics. So we're collecting every single page load, the timing on every image load, which views inside a mobile application people are looking at, how long it takes to be ready, how long network calls are taking from mobile devices, how long Ajax calls are taking. All of this stuff's going in there as well as the crash reporting. So we actually have the two pieces in there, which dials up the data volume by a couple of extra orders of magnitude as well. So there is a lot of data flowing through there, and we've done a lot of work to try and keep the performance pretty workable. I won't lie, we typically run through a fairly consistent development cycle of 6 months where we feel like the system is doing really well and it's nice and fast and performant, and then 6 months of, oh goodness, it's all burning down. Let's rebuild the aircraft halfway through the flight, that sort of thing. So, yeah, there are a lot of interesting challenges. We're processing probably a couple of billion data points a day now through the platform. And for the most part, and I know we're going to dig into this a little bit more, for the most part, a lot of the system is built using Microsoft technologies, using the .NET framework, .NET Core. There's a little bit of Go in the mix there. And then there's a reasonable amount of Java as well with relation to some of the data storage technologies that we're using.
You're on AWS?
We are on AWS at the moment, yes.
Okay. So you've got all these requests that are coming in, and they're making their way through your service infrastructure. Well, first they're getting load balanced, then they're making their way through your service infrastructure, and then they're getting put into these various data stores so that the users can understand the performance and the crashes and what's going on in their applications. So let's start with that load balancing layer. As you described, you've got a whole lot of different types of requests. You've got a high volume of those requests. What are you doing at the load balancing layer?
So we're definitely making use of some of the load balancing technologies that AWS provides that are fairly common across most cloud providers. And then behind that, we have effectively an auto-scale group of EC2 instances that are running our API layer code. And so they basically receive the data and then they verify a couple of quick things. So making sure, for example, that the client API key is valid, checking a couple of rate limiting things. If somebody's, paying for a certain level and they're way over, we manage that. And then otherwise they put it onto an internal queuing system to be lifted and processed. And so that API layer used to be in Node.js. They're not particularly massive boxes. They're relatively small. And we ported that to Microsoft's .NET Core framework about a year ago, and we managed to increase the performance of that API layer by more than 1,000% on there. I think it was actually about 2,000% improvement in throughput, which alarmed a few people who thought we must just be using Node wrong, which I disagree with them on that view. But .NET Core has been a fantastic win for us on that API layer. It meant that we could process more per API node and therefore decrease the number. We didn't decrease it right down, but we brought it down enough that we could still have enough sort of servers in the warm pool, if you will, to auto-expand quickly if we needed to. So that's the first layer.
When you say API layer, does that mean that it gets these requests hit a load balancer first, and then the load balancer spreads them through the API layer, and the API layer routes the requests to different queues, or is there a queue in front of the API layer?
No, it's the standard ELB related stuff going to an auto-scale group, then what we do is we maintain a queue per application that we're tracking. And this allows us to solve for the noisy neighbor problems. You wouldn't want to be using a service where just because somebody else was using it heavily, it impacted your performance. And so by doing it on a per app level, one, it gives finer grained control of rate limiting if needed, but it also means that if you're doing a striped worker approach where you're fetching X number of items off a Y number of queues at a time, you don't have to worry so much that one queue might be backing up a little bit. It's not going to impact your processing time performance.
What are you using for queuing?
We're using Rabbit at the moment. Quite comfortable. We're not using like the AWS built-in queuing services. What we've typically found with a lot of the services that the cloud providers have is that they're wonderful if you are either not money conscious in the least or not doing a heck of a lot of operations with them. So frequently we end up where we'll do something like run our own instances running things like Rabbit rather than be paying per 1,000 requests to a queuing service, that sort of thing.
Any reason you went with Rabbit over Kafka? I imagine the simplicity, I guess. It's
the simplicity. There's also just the way that we then pluck things off the various queues there. We've had some internal conversations about moving some things to Kafka over time, but it's just not been a sort of a burning need at this stage because we don't do too much in the way of advanced routing. The way that the worker processes are architected, they kind of pick off a piece of work, and then I think there's only really a couple of extra layers around the persistence side, so it would be a pretty short workflow even with it in there.
Okay, so you've got this high volume of events that are coming in, they're getting load balanced across API servers. The API servers are routing those requests to the appropriate queues based on maybe what the request is. Is this monitoring around image loading? Is this a crash report? Based off of those different event types, you will have routing to different API endpoints, and then which means different queues and different workers. Do I have it right?
That's correct, yeah. I mean, you can kind of imagine like any software development process, the two products came together separately, so they do have their own processing models. They're very closely aligned, but yeah, basically different API endpoint, different queues, different workers. The data storage, however, it often gets unified because one of the driving things that we wanted to improve in the space of monitoring and ops is that there's a lot of silos of data. And we hate having silos because we think that the real insight lies in being able to overlay this information together, bring it together in one place. So the data storage is kind of fairly unified.
Got it. The workers that are pulling these events off of the queues, what are they doing exactly? Classify kind of what the workers are doing.
So we'll start with the crash reporting side. What they'll do is they'll pop off the record, which is typically a JSON blob. They'll inspect that to see what the sender was sending from. So basically the provider, was it JavaScript, was it Java, C# and whatnot. And the reason that's important is because we then will pick a grouping or classifying strategy based on what it came from. And the reason for that is that we want to group up errors. If you had 10,000 errors but only 4 bugs, you'd actually want to see the 4 bugs with the counts next to how often that occurred. You wouldn't want to get 10,000 items to look at in a list. It wouldn't be very manageable. So we do this grouping, and those groupers themselves, they have a lot of logic in them. So for example, our JavaScript one is smart enough to identify that even if an error looks wildly different between, say, Firefox and Chrome, they're actually the same fundamental bug. And they'll align things like stack trace lines and messages and be able to bundle them together to make sure that you've got a very actionable workload. Then what they're going to do is it's going to update a couple of various counters in places and then look to persist various bits of data to the different data stores that are needed. So the major data store that we have is an internally built storage engine, which overlays on S3 but does a whole bunch of smarts to make fetching of data more efficient, the roll-ups of data. It's kind of a little bit like the Hadoop file system in a way where it's bundling things up into content blocks to make it much more efficient, both on cost basis and a computer performance basis to load data faster for our customers.
Sorry, so what exactly is getting stored in that Hadoop-like file
The
system?
entire raw data. So for everything that Raygun receives, we can give our customers 100% of the raw data that they had in there if they wanted to see it and go to that level. A lot of players in this space will give you averages and charts and not really let you access the raw data. We store just hundreds of terabytes worth of data that our customers, especially larger customers, frequently like to pull out and feed into other systems. And then lastly, in that working process, it will also trigger a couple of internal notifications, and that will mean that depending on what the customers have configured, do they want alerts to Slack, do they want to get an email, what are the rules around that? But that's handled by a notifications worker. So that's the one time it pops something back onto a sort of a pub sub type system internally.
What would be an example of one of those raw data files, and what would lead to the creation of that raw data file?
So the raw data file would be the JSON blob that the Raygun service received. So the entirety of the error context, everything we picked up at the time of the bug occurring, environment information, server information, depending on where it's from, iOS, let's say it might be the device information, as much as we can collect at the time of the error to try and help our customers more rapidly resolve an issue. And the plus side of that is because we make all of that information available, when we do have some very large customers who have very serious security requirements, and we can say, look, you can see literally everything we've collected. There's no hiding it behind things. Have a look at that. And then our SDKs include filtering. So if there is some piece of data that they don't want to provide, they can filter that out. We, of course, have some defaults in there around things like credit card numbers and social security and whatnot, but they can always add more.
So when you're talking about the events that are doing monitoring, like when you're just monitoring the application, but a crash has not occurred, does the storage model differ?
The storage model doesn't change a whole lot. It's a fairly consistent story in there. We don't have to do things quite so much around the grouping, like we might group based on URLs, which is pretty straightforward to do, or a page and activity names inside of a mobile app, but it's fairly consistent.
Dice helps you accelerate your tech career. Whether you're actively looking for a job or you need insights to grow in your current role, Dice has the resources that you need. Dice's mobile app is the fastest and easiest way to get ahead. Search thousands of tech jobs, from software engineering to UI to UX to product management. Discover your worth with Dice's salary predictor based on your unique skill set. Uncover new opportunities with Dice's new career pathing tool, which can give you insights about the best types of roles to transition to and the skills that you'll need to get there. Manage your tech career and download the Dice Careers app on Android or iOS today. You can check out dice.com/SEDaily and support Software Engineering Daily. That way you can find out more about Dice and their products and their services by going to dice.com/SEDaily. Thanks to Dice for being a continued sponsor, and let's get back to this episode. So let's talk through the ingestion and the processing of a single crash event. So a crash event occurs. You've got this JSON blob that contains a ton of information about the application at the time of the crash, and it gets queued up, and then it's getting processed by the worker. And what's the unit of deployment for these workers? Is it a virtual machine? Is it a container?
No, it's not containerized yet. We are still a little bit old school on that front, where we use Octopus deploy, and we deploy updated versions of these services to a cluster of different machines. What we've found is that while there is some spikiness to the volume, because we're very much a global business, there's only a short period of the day really where it's particularly quiet because we've got a lot of customers in Europe and a lot of customers in North America and a lot of customers also in Australia. So for the most part, it spikes a little bit, but it's more one customer spiking doesn't typically cause us too much stress. It's more the overall daily sort of ebbs and flows. So we have a fix set in there with the ability to rapidly add additional instances with that software on there, and then they will pick up different sections of the queue to manage that scaling there.
These workers that are processing the JSON blob. So what kind of work are they doing in order to process that before they put it into the storage layer?
So that's where they're doing things like reading it in and analyzing for the grouping, triggering notifications to customers, updating various counters for people, because obviously we don't always count everything up in real time. We do for the most part, but they'll update various things. They update the customer usage information so that we understand how much customers are utilizing the service. They don't have to do a heck of a lot, to be honest, before they're passed off to the storage subsystems for people to then come into the application and actually analyze what's going on.
Right. Yeah. Okay, I got it. So they're just kind of updating things that might be viewable in a dashboard, or just stats, and then they're rapidly passing it off to the storage layer. And these workers are written in .NET, and I think did you say you said the API layer you rewrote from Node to .NET. Were the workers always in .NET?
The workers have always been in .NET full framework, not .NET Core yet. We probably will be moving them to .NET Core at some stage, but it's not a hugely high priority right now. We also do have a little bit of go in there around how we manage the symbolification of crashes from iOS, and that's just a small service that's orchestrating the symbolification process.
What's symbolification?
So in iOS or in an unmanaged language like C or C++, when you get a crash, you get a memory dump, right? And it's not readable to a human. And so with iOS and those other languages, that's where you get the symbol file. So maybe a PDB file or a DSIM file for iOS or Xcode generated outputs. And basically, if Raygun has copies of those, which we have integrations to automatically pull them up for people, we will automatically go, okay, we've got this memory dump and we've got this symbol thing. Let's do some magic to turn it into a human readable stack trace so that the Jeff can read it and go, oh, it was line 49 of this class and this function, rather than here's a raw memory dump of hex values that mean nothing to me. So that's what symbolification is about.
I see. So just talking about the .NET workers that are getting these JSON blobs, they're making some updates to counters and things, and then they're storing the JSON blob in your S3. I think you said S3, right?
It's backed off of S3, but yeah, there's a layer in front of that does a lot of smarts for how we roll up. And like I said, it's very, very similar model to the Hadoop file system. So let's say we've got 100,000 errors come through. We might roll that up into a single block that we can then index and pull data out of very, very efficiently. Oh. But we can pass that block around so we don't have to make 100,000 requests to S3. We don't have to worry that the latency per request would kill performance because we've done a lot of analysis to find what the ideal size is for our infrastructure to make sure we can get a lot of data very quickly, cheaply, efficiently.
Wow. Maybe we could talk about the file system a little bit later.
Yep.
Because that sounds like a pretty interesting conversation. I'm sure implementing that took a lot of work.
It did.
Yeah. Yeah, we did a show recently about Keybase, which is kind of this new identity platform, but they have a file system. They wrote their own file system, and it was just always, I don't know, talking about writing your own file system is always a challenge, even if you're building it on top of S3, I'm sure. But as far as the workers, they are processing these large JSON blobs. So I saw a talk that you gave about the garbage collection and the memory management that you have to do in your .NET worker layer. Is the main reason for that garbage collection, the work that you did around garbage collection, is that because of those large JSON objects?
Yeah, so you're talking about the video where I talked about the source map processing worker, is that correct?
Yeah. Yes.
So in that one, and we'll sidetrack a little bit into that story because it was quite fascinating. So source maps are very similar to effectively a symbolification process where when you minify your crash reports when you minify your JavaScript and you combine files, right, you're used to seeing those errors that will say something happened on line 1 at position 34,000, and you're like, well, I don't typically write my programs as a single line 34,000 characters long. That's clearly a post-minification process on my JavaScript, right? And so a source map file can be generated by most minifying engines, and that allows us to also unwind it back to the original version of the code that you had. So it would say, actually, it's in line 490, column 10, here's the code. So it makes it easier to debug. Without them, it's kind of a pain in the butt. And this was a few years ago now, and I remember talking with our CTO, and he was like, oh yeah, we've just put in our third machine for our source map processing. I'm a nerdy guy, and I was like, really? 3 machines for source map? How many are we processing? And he's like, well, we're doing millions and millions of them a day. And I was like, oh man, I don't want to keep adding machines. I want to make this faster. And so at the time, we were using Mozilla's source map processing engine, which is open source. And I looked at this thing and I was like, okay, I can probably port this over to .NET. And so I did. And then this was like a weekend project for me. And then I ran the profilers like crazy to get this down. And ultimately, we ended up where we moved the source map processing to a .NET service where a single machine out of the 3 could process our entire day's volume in like 1 hour or something like that. And so that talk that's on the Channel 9 website, basically I was talking about the ways that I approach the performance handling for that, and there was some low-level stuff. But whenever you're building on a language that has a garbage collector, so anything like Java or .NET are the 2 most common ones today, but there are others, you really need to be aware that the benefit of having garbage collection is that, you don't have to worry about the allocations and deallocations and things like that. But there is a cost. Everything comes at a cost. And so one of the things that's been fascinating is that because allocations are so cheap and easy to do without thinking, is a lot of developers are allocating memory like crazy, not realizing that there's a huge performance penalty in that. And of course, you're thinking, well, hang on a minute, isn't memory fast? Isn't that how our databases are getting fast? Because we just put the data in memory and that makes it quick. And that's where you've got to remember that, accessing the L1 cache on a CPU is about half a nanosecond. L2 cache is about 2 nanoseconds. And then say your main system RAM is more like 100 nanoseconds. So if you're actually writing and creating data all the time in memory and going backwards and forwards, one, that's actually quite a bit slower. And secondly, of course, you've now got this additional processing layer, which is your garbage collector that's having to mark and sweep the memory or however it wants to do the handling of clearing that RAM from time to time. But it's kind of ended up where us as developers can be very, very efficient at writing code in a garbage collected world, at the downside that we often don't think too hard about it on how much memory we're actually allocating. And so when I was working on that particular little service, I was kind of going, well, I want to make sure I don't allocate much memory. And I suspect you're referring to the fact that the JSON data, so the way that a source map is structured is in JSON. And there were many things that we looked at, which was like, hey, well, what if we didn't actually deserialize the JSON data into a first-class object? We actually only need to read it once, and we can just we already have it read in as a string. Why don't we just read it like it's a character array and just mark the points we need and pull out the data as we need it? Things like that, which dramatically accelerated the rate of handling those source maps. And then also, if you watch that video, I think I go through about 5 or 6 different things. Like, for example, hey, well, if we only need to parse the source map 50% of the way, the plus side is we don't even need to read the next 50% of it. So, the best way to make code fast is to do nothing at all. And so there's a lot of those shortcuts. There were things like not serializing the object. There was all sorts of stuff went in there. And I remember actually bugging my friend Nick on that weekend on Skype because I'd be like, hey, I've just shaved off another 25% of the processing time, and all this. The only thing that makes me sad reflecting on that time was that I don't know if it was out at that stage, but there's an amazing tool in the .NET community now called benchmark.net, and you can do in a very similar structure to how you would write your unit tests. You could just augment things with benchmark attributes, and it will tell you, for example, how much memory is being allocated, what stage of the garbage collector, it does all the statistical handling for median times, mean time, standard deviation, what's the baseline of the machine, all sorts of cool stuff. I didn't have that at the time. I was just using a full desktop profiler, which was still good enough, but I kind of need to go back and have a fresh set of eyes look over it and probably port some of those tests over to benchmark.net. So sorry, that was quite a segue, but yeah, that's the sort of thing we look at.
No, it's right. It's a good example. So to be clear, so you've got this large crash report essentially, and you're trying to figure out how much of this crash report do we actually need to pull into the worker, or how much do we? Well, first of all, how much do we need to deserialize?
Well, no, just to be clear. So what happens is we always do everything with the crash report, but in this case, you're saying. Okay. And if it's JavaScript, and if there's a source map available, then we need to do basically a post-process on the original stack trace to make it more human readable. So it's only it's more like an if statement with a few variables in there get checked, and if that's the case, then go and do this extra piece of work. Similarly for iOS, for example, if somebody hasn't provided us a DSym file, well, we can't symbolify it, right? So it just go through as is. But if we have it, we want to make sure that we enrich the stack trace to make it human readable with the symbolification process. So there's just a couple of little edge cases in there, that it was quite involved building out Raygun. It's a fairly mature platform these days. There's a lot of things it can do.
Yeah, and so you're not control, because like I worked at a place one time, this options trading company, and a similar, like any trading company has a really high volume of stuff that comes through it, and there was a lot of work that would go into tweaking the garbage collector in Java. And this was my first job out of school, so I had no idea, like, how do you do any garbage collection tweaking? But I would see these people, these engineers, and they would be, pulling up these Java tools for, like, assessing how much memory is in the, I guess, these different, like, the Eden space, or the, these different, like, garbage collection tiers in Java. But that's not what you're doing here. You were just, basically, you were before stuff gets pulled into the place where it's going to be managed by the garbage collector, you're saying, well, do we even need to have this data be pulled into memory? Or do we even need to create this object in memory? Is that right?
That's absolutely correct. So to your point there as well, like Java seems to have a few more different garbage collection options out there. And in .NET land, there's primarily like a client garbage collector and a server garbage collector. And then there's obviously new versions of the garbage collector that come with different versions of the framework. So it's not quite as rich as the Java community. You can also control in a sometimes non-deterministic way how some of the things, like giving hints to the garbage collector in code. But on the whole, and this has actually been a huge driver for a lot of the performance improvements that Microsoft have made in the .NET Core framework, is that if you just don't allocate the memory, then you don't give work to the garbage collector, right? So if we can reduce those allocations as much as possible, the code actually goes faster, because memory allocations, one, are expensive, and two, you have that somewhat hidden cost that the garbage collector now has more work to do as well. So by focusing on the number of bytes that get allocated by a piece of code and bringing that down, all the better. And so we did a lot of that sort of work early on, and we're still doing that today. Literally, one of our team members, Jason, is working on some of the way that we do grouping code for the real user monitoring data around the pages. And like now it's fairly common where he is posting pull requests that actually include the benchmark.net output of before and after to say, here's the time it took, here's the bytes that were being allocated, and here's where it is now to demonstrate performance changes.
How much money can you save on these kinds of performance improvements? What sort of savings does it translate to?
Well, so we've had some fairly significant wins in the past around these improvements. I mean, at the time, back years ago, when we did the source map one, for example, I think that was a relatively quick saving of about $1,000 a month. We were really, really small at the time. But further to that, because it was only using a fraction of one of the servers, we could also put other things on there. So there were additional savings there. We find that today most of our costs us are actually driven by the data storage side of things, not the compute intensive side. And so that's where we're starting to look at things like how do we, that's partly why we started looking at like our own storage subsystem a couple of years ago. And that was a huge win for us. That actually saved us, I think it's probably now cumulatively saved us several $100,000 since that went into operation. Because, of course, if we bring something down by, say, $10,000 a month, well, a year later, that's $120,000 that's been saved. It's not like we can stop doing data storage next month. It just improves things. So we're always looking at that. And I think that's one of the strengths that I can help bring to our business as being a CEO with a tech background, is I can sort of have these conversations with our CTOs, my business partner, and we can sort of weigh up, hey, is this a situation where we just want to throw servers at it? Or do we actually have, and I consider performance things a form of technical debt as well. Even if the code is reasonably fine, hey, maybe we could just make this more efficient and not need to go and get a bunch more servers. Usually it's dependent on what else is going on in the business at the time. Maybe we're working on, when we were building out the real user monitoring system, obviously a lot of our engineers were busy working on that. And so we didn't have the bandwidth. So we just had to say, look, we're going to throw more servers at it for now, make a note, we'll go back and tune this stuff up. But it varies. I do think that's a huge thing, which is evaluating when to look at performance improvements. I see a lot of engineers, they'll either think that the performance issue lies somewhere where it doesn't, or it's not actually a performance improvement that does make the business save money, or it's not something that impacts the customer in a positive way. So they're always important things to consider as well.
Do you have a product that is sold to software engineers? Are you looking to hire software engineers? Become a sponsor of Software Engineering Daily and support the show while getting your company into the ears of 24,000 developers around the world. Developers listen to Software Engineering Daily to find out about the latest strategies and tools for building software. Send me an email to find out more. Jeff@softwareengineeringdaily.com. The sponsors of Software Engineering Daily make this show possible, and I have enjoyed advertising for some of the brands that I personally love using in my software projects. If you're curious about becoming a sponsor, send me an email, or email your marketing director and tell them that they should send me an email. Jeff@softwareengineeringdaily.com. Thanks as always for listening and supporting the show, and let's get on with the show. And generally, I think from a strategic standpoint, it makes sense to look at saving money as a core tenet, because you're not exactly in a business where you have complete dominance over the field. You're not like Google or Facebook where you can just say, okay, we don't really need to worry about competitors. We'll just buy all the stuff that we need because we sort of have a monopoly. We're just trying to cement that monopoly. There are some competitors in the field, and so keeping the price in a competitive tier is probably pretty important to you.
Yeah, I look at it more from the you're right. We're not a Google or a Microsoft. We're working our way there. One of the things that's a bit different about Raygun to a lot of players in the space is we're not a hugely VC-backed company, right? So we're not just burning cash for sake of it. We actually have a very strong business, unlike most of our competitors that are bleeding cash trying to, soak up customer count. Raygun actually is a very stable and still very fast-growing business. And the way, again, that I look at it is any dollar I'm not giving Jeff Bezos is another dollar I can spend on growing my business. So, that's sometimes our logic is, gross margins in a business. So you look at what's our cost to serve a customer, how much do we spend on support, infrastructure, credit card processing, all that sort of stuff. And that's going to be a fixed amount that we have to pay every single month to support our customers. Well, the smaller I can make that, right, the more I can spend on marketing, the more I can invest in getting more engineers to develop additional features that add value to our customers, all of that sort of stuff. I'm more driven by how can we grow faster and help our customers more because we're efficient, as opposed to just saying, hey, can I make it the cheapest product in the space? There are cheaper products in the space, but the first thing that happens when you dig under the covers is, oh wait, you're not actually storing all the data. Oh, you're heavily sampling. Oh, I couldn't tell you how many hundreds of customers have moved to our platform because they were like, well, it was kind of like trying to explore a cave with a candle versus having floodlighting. If you don't have all of that data, it's quite difficult. It's kind of like there's tools, and I'm not picking on specific competitors here, but in the wider monitoring space where all they talk about is averages. Right, so because we have all the data, we'll often give people the P90s, P99, the distribution data of what's going on. And the great analogy that I've always loved about why, if you are looking at averages, you are looking at lies, is, let's say, Jeff, you and I, we go and fill a stadium with homeless people, and then we invite Bill Gates in. Well, on average, everybody in there is a multimillionaire. Right? Averages are utter lies. And so if you're using any tools that are monitoring things and they're giving you here's our average response time, well, you can be sure probably no one experiences that actual time. You need to see the wider distribution. And that's where we kind of see it as, hey, we're at a point now where the costs of storing large amounts of data, especially if you're quite clever about it, is not a huge number. It still has some cost, but yeah, you want to store it all.
Yeah, well, and just another note on the whole competitive landscape of software. My perspective in reporting on these different things is even the products that look like they're in very competitive spaces. Like one of the early narratives when I was starting Software Engineering Daily was like, who's the cloud provider of choice? Is it Azure? Is it Google? Is it AWS? And as you drill into it, you realize, oh, cloud computing is actually a tremendous blue ocean space where there is room for lots of different people to arc out what they want their domain specificity to be. And as I'm sure you have come to realize in your business, is pretty much the same thing when it comes to monitoring and crash reporting, where this is pretty much a fundamental thing that people want in their applications, and there are just different flavors of it that make sense in different contexts.
Yeah, absolutely. There's no one right thing for everybody. That's sure. Absolutely correct. I mean, there's plenty of free tools people can try and use and things like that. I mean, that would be another, though, usually false economy. Let's go and try and set up something for free and manage it ourselves rather than spend a couple of dollars that I see. It's usually a bad idea.
So this file system that you built on top of S3 to store all of these large files, like these large, I guess, basically dumps of what's going on in a system when a crash occurs. The reason you built a custom file system on S3 was, if I recall what you said, is to categorize similar crashes that occur, and then you want to put all these similar crashes in a block together so that block is easy to manage when you're moving it around S3. Is that right?
Yes and no. It's not so much that the errors have to be similar. It's stored in a chronological order, and then what we maintain is several layers of storage. So we obviously have in-memory, then we have local EBS SSD backed stuff, and then we have S3, and we cache the hot data first, and then it's rolled up into these blocks. So let's say rather than having, I'll use some round numbers, let's say there was 100,000 crash reports, and they stacked up to, let's say, 100 megabytes of data. So we put them into a single block. We attach our own metadata to that allows us to quickly be able to pick things out of that block very, very fast, and also reduce some of the space sizes as well. And then they get stored in various cached buckets all the way down. So that way that the warmest data is obviously loaded very, very quickly, but it also means that there's a process there that can handle massive spikes in data coming through, and how that then blocks things up. And then we can do that longer-term archival storage. So, a Raygun customer can come in and say, hey, I'd like to export the last, 6 months worth of our data, and they might have had, 40 million errors a month occurring, which is not unheard of, and it might turn into a multi-gig download for them, but we can actually fetch all of that data out of there very efficiently. You can kind of imagine, even with what the cost of GET requests against S3 is, we probably wouldn't want to be storing hundreds of millions of individual crash reports, and having to pull them one by one would just take, one, too long, two, cost a fortune, and three, it's actually quite slow to hit S3 by default if you were just fetching customer data from there, which is why we like to keep some of the more recent data warm, closer to the source. So it's kind of got a classic caching strategy in there that's layered.
What are you using for the caching? So
we manage that ourselves for the disk storage in S3, where it's just the blocks will get moved around based on, the temperature, if you will. If that's recent data, it's in there. For the caching that's done in memory, we are effectively just using the .NET cache providers that are built into the framework, which, to be honest with you, I haven't looked in recent times at what their various eviction strategies are around that, but it hasn't been an issue for us, so I haven't had to look very deeply at it.
I see. Okay, so the workers will hand off the file to S3 as well as to an in-memory cache elsewhere?
No, they just pass it straight through to that storage processor, and then what it'll do is make sure that it ultimately ends up in S3 as part of a block that's been processed, as well as in various caches too. So let's say, Jeff, you get an email that says, or a Slack notification or HipChat or whatever, it says, hey, this new error has occurred. You want to click on it, you want to go into the Raygun app and see all the data right there. It may still not have made it through to S3 at that point, but it can be served out of one of those hotter caches leading up to it, and that storage service is well aware of where it's at. So we want to get to the point where if you get a notification, it might be within 2 seconds, 3 seconds of the error actually occurring, and you can see the entire report within the application. So we used to get more people, early adopters were like, holy cow, this is amazing. Sometimes I get the notification of the error before my error page is even loaded. So that was always our goal.
I see. So the reason you cache it before writing it to S3 is so that it's in a place where the customer can easily and quickly access it, or like just on the fly, like shortly after the crash has occurred? So
they can access it quickly, and secondly, because we do want to collect up in blocks of data, so maybe, like I say, it could be 100,000, 10,000, depends on the size. We want to then bring them into a single writable chunk that then gets written to S3. So it may not actually get to S3 for a few minutes, and we don't want to have you wait until it gets to that stage. We want to be able to give it to you very quickly. That's, again, part of that whole idea that if there's spiky ingestion stuff, that service, we basically don't really have any issues with it. It just kind of quietly sits there and pulls the data back through. Yeah.
So you can imagine a scenario where one of your customers has like 10 or 15 crashes that are super similar within a single minute, and you would want to batch, as those crashes come in, you would want to just keep them in memory and then batch writes of 10 to 15 crashes out to S3 in these blocks.
Yeah, absolutely. Yep. Although the numbers are a lot more than 10.
Okay, I can imagine. And again, sorry to drill in this. I find it interesting, but what's the advantage to getting those in blocks together?
Because S3 is going to, one, charge you on the number of writes you do. So if I write 1,000 1K blocks and I write one 1,000K block, one of them is 1,000 times more expensive than the other. So it sufficiently reduces our writes. Secondly, there's obviously a latency to any request, whether it's write or read or whatnot. It's a round trip. And so we did a bunch of analysis ourselves on finding what the optimal block size was that would give, let's say you hit a really old error, right? And it had to come out of the S3 block thing. What was the time frame that we thought was acceptable for you to have to wait for that crash report to be ready? And it worked out. I mean, it was basically a couple of seconds. And so we measured and built out an entire chart that said, okay, based on file size across S3, what's our time to get this back? And so we used that to define the size of the block. So, and then lastly, because, one, it reduced the S3 costs. It also reduced the latency overhead because we weren't having to pull things. It also enabled us to do things like allow customers to export massive amounts of data. And then it also sped up the time at the front end with those caching layers because customers didn't have to wait for it to be written. So way back when we first launched the service, it wasn't uncommon that you would get a notification that would say, hey, Jeff, this error occurred, and you'd click on the link and it would say, hey, wow, you're really fast. Wait a few moments for us to have to get that data stored, and it'll be ready in a moment. We wanted to get rid of that, which we did. So yeah, it was basically a triple or quadruple win. So customers got faster service, both in terms of day-to-day usage and time to first error visibility. We saved a bunch of money on the back end, and it unlocked a bunch of features that would probably have been cost prohibitive either on price or performance using the older model.
So you're not only storing these crashes on S3, but you also want to index these, at least some of the metadata perhaps about the crash in Elasticsearch, or probably keeping them in other file systems or other databases also. Can you talk about the multimodel database situation?
Yeah. So for example, we have a search system using Elasticsearch. We have a time series data store, and then we have a relational data store, because if you try and use one data store for all those different types of information, you can end up tying yourself in knots. So we have these different data stores that where information is getting stored. Well, we also have Redis in there for a little bit of live data to show people what's going on. So it really just routes to how we want to present the data to the customer.
Do you have what's your pattern for writing to these different data sources?
Well, it effectively, so let's say it was a crash report. That worker is going to ensure that it fires off a indexing job to Elasticsearch to index it for search. It's going to send the data off to the storage system for that long-term storage and the raw error report. And it's also, in the case of crash reporting, it's going to update some various counters in a relational database for the group level information. How many times this occurred, how many users were affected, that sort of thing. We do a lot more time series data on the performance side of things. And so in the performance tracking system, that would also fire off we use Druid for our time series data.
Oh, yeah. Cool. Okay, so just to refresh people on the end-to-end architecture of this system, because I think this has been a great lesson so far in how to handle high volumes of events. So I'm using my podcast app, or some user is using the podcast app that I developed. I'm the developer. I'm using your system, Raygun, to see the crashes that occur. A crash occurs on my user's podcast app. The crash report is sent in a JSON blob to Raygun servers. First, it hits the load balancer. The load balancer sends that request to an API. Load balancing requests across API servers. So that request is routed to an API server. The API server routes it to a queue in front of workers that process crash reports. One of the workers pulls the crash report off of the queue and starts to process it, and it's basically figuring out some aspects about that event in order to figure out what to tell the storage worker, I guess, and then it hands it off to the storage worker. The storage worker puts it in Elasticsearch, MySQL, Druid, and batches writes of this type of crash to S3. And then the user can access all of these different data sources. Is that correct?
More or less, yep. You've got you've got a 99% right. There's a couple of those things happen in the actual crash worker, but for the most part, yes. Yeah. Okay. It's quite a there's a lot of moving parts.
Yeah, well, it sounds like a pretty interesting system to wake up every day and work on, because I'm sure there's lots of performance tuning things that you can do throughout that process, but at the same time, a lot of it seems like it's probably a stable architecture.
Absolutely, and so it is relatively stable, and this goes almost full circle back to how we started, which is what we typically find is for 6 months, the system is just absolutely, rocking it along. It's really good. And then our fantastic customers and sales team and things like that keep closing more and more business, and some little cracks start to appear, and we kind of go, oh goodness, it's time for the next round of work in there. So, it comes and goes, but they're certainly really fun problems, and they. I'll be honest, back when I first got into the industry, I used to think of, working at Google and the scale of the problems. And, we're definitely not at Google's scale yet, but it's one of those ones where you are starting to go, oh, how could I cost effectively, juggle a few petabytes of data? And how can I real-time query some of this to give our customers the visibility that they need, and sub-second response times if they want to slice and dice it, and things like that. That's the high-quality problems to have to think about.
Totally. So you talked earlier, like you don't necessarily have bursty workloads, so because you have stable traffic throughout the day.
Well, it's more that we've got to the point where the bursts are, when it was our first 100 customers, right? Because we've got thousands of organizations now using us. But when it was earlier on, you might get one customer and go, oh my goodness. But we have sort of evolved to the point now where there's probably at any one point 2 or 3 or 10 customers that are having some massive meltdown. But now it's still not, that significant to us to have to deal with it. Yeah,
it's more like steady customer growth is a bigger concern of yours than bursty customer usage.
Yeah, absolutely. Yeah.
Well, can you talk about, like, what are some of the things that are starting to break? Like, why? Because, the way that you've described the architecture so far, it seems like, just horizontally scale that to the moon. Why not?
Yep, absolutely. So examples of that would be, like I said, where I mentioned the worker layer, where we can reasonably quickly spin up an additional instance to add additional work processing. We'd actually really like to try and move it to more of a containerized workload that auto expands and does all of that and is a little bit smarter, that sort of thing. We are in the process at the moment as well around some of those data stores, which are horizontally scalable, at just making them be a little bit more programmatically driven, if you will, so using various ops tools to make sure that we can spin up and shut down instances based on what's needed. So we're doing a bunch of work around that. And to be honest, that's a little bit about cost optimization and more just about the maturity of the infrastructure and taking it up a level in there. So there are the areas where we might say, hey, maybe we're adding one server every couple of days. We need to make sure that this is sort of fall off a log easy and almost anyone on the team can do it, rather than saying, well, there's a couple of people who manage the AWS account and they can go in and manually run up something off an AMI. Things like that we're improving around. We also continually just find various areas to improve. So, for example, that storage system that we've talked a lot about today, we had our initial data structure for those chunks, so that's been in operation for a few years now. And we actually have a V2 version of that data format for the chunks that basically gives us an extra order of magnitude improvement in response times for customers, because we were finding, hey, now that we actually have millions and millions of these giant chunks, what can we do to improve upon this? And how can we append extra metadata to them to provide extra querying and filtering? So there's things like that just sort of, get slower with time. We want to improve those. Yeah, range of stuff. There's also new features always add additional demand. So like, when we first put in that storage system, we went, oh, cool, now we can build an export feature really easily. So we put that in. We do have APIs available for querying data. Specifically, enterprise customers like to do that a lot. And so, hey, maybe there's a query that's just not very efficient, so we need to work on that. It's just every day there's always little extra bits. And that's where monitoring is so important for understanding where are the hotspots, where is our time going.
All right. Well, I know we're nearing the end of our time. We've talked about pretty much the high level view of the architecture. Since you're the CEO, tell me a little bit about running the business. Like, just to close off, what are some non-obvious aspects of running Raygun?
Well, I guess as a background, I obviously have learned how to build out a sales team, which is what we've got here in Seattle. So I moved to America to build out the sales team in the US, but we're still headquartered in Wellington, New Zealand. So that's been interesting. Also marketing. So the marketing team reports through to me, and they've done a wonderful job at getting the name out there. Credit to, I think it was Freya has been working with you as well,
That's right.
Jeff, on getting on your radar.
Yeah, she's great.
So Yeah, understanding all that. Yeah, I think she's fantastic, which is good. And we've just, learning the different areas, and that's kind of the day-to-day thing. Also managing, being on a board of directors, answering to them, understanding investment rounds. Like, you basically end up becoming the ultimate generalist, really. The thing that I've found hard is the transition from being a software engineer. I think people naturally will always fall back to what they're most comfortable with. And so a few years ago, what I would find is that I would frequently end up writing a bit of code for the system. And it was like, you know what? As much as I enjoy doing that, it doesn't have the biggest impact for the company. We've got a big team of people far, far smarter than me, to write code. Why am I doing this? And I kind of realized that it was because I'd either be putting off something that I needed to do that was a bit more difficult. And so I actually ended up going out and I moved to a 13-inch laptop. It was bloody awkward to write code on. I couldn't run Visual Studio instances all over the show. And it was a forcing function to be like, you know what, if you're the CEO, generally speaking, you should probably be fine with like a Chromebook and possibly even an iPad. You've just got to send emails and use the internet, right? So I had to force myself out of that comfort zone a few years ago. Now, to be honest, I still absolutely love to code. I have a beefy as hell machine at home that I do various bits and pieces on in the weekends. And, I've been exploring things like TensorFlow because I want to make sure that I still have a good, strong understanding of this. And I love talking with our tech team about these performance issues. Gets me off. I love high performance software, but that was a difficulty. Is the business would grow a lot faster when I wasn't writing code because I'd be focused on the growth. That was a big transition. And I guess lastly to that point, coming from engineering land, we tend to think as engineers that we're like the smartest people in the room. Bad news, folks. We're not. There's smart people in every category of the business. They're all delivering value in different ways. I think there's a certain argument to be made that perhaps the Dilbert cartoons for 20 years have perhaps overinflated our egos about our talents versus other people. But,
I completely agree. I mean, try putting the engineers in charge of enterprise sales, and you'll see what happens.
Oh, yeah.
You'll see how smart they are.
I still remember when we first got into some of the pay-per-click advertising, and there was a couple of engineers who were like, this will never work. I've never, ever clicked on an ad. And I was like, you think you've never clicked on an ad. You think you've never been, and it's like, guess what? It works really well.
Yep.
But yeah. And I'm not just saying that because now I'm officially the pointy-haired boss, just to be clear. Though I possibly am the dumbest person in the room. But
all right, JD. Well, it's been great chatting, really good show, and look forward to hearing more from Raygun in the future.
Yeah, absolutely. It's been my pleasure, Jeff. I really appreciate it. And if you can't tell, I can wax lyrically on just about anything. So I'm happy to do another show sometime. Right. Thank you.
Sounds good. Simplify continuous delivery with GoCD, the on-premise, open-source, continuous delivery tool by ThoughtWorks. With GoCD, you can easily model complex deployment workflows using pipelines and visualize them end-to-end with the value stream map. You get complete visibility into and control over your company's deployments. At gocd.org/sedaily, find out how to bring continuous delivery to your teams. Say goodbye to deployment panic and hello to consistent, predictable deliveries. Visit gocd.org/sedaily to learn more about GoCD. Commercial support and enterprise add-ons, including disaster recovery, are available. Thanks to GoCD for being a continued sponsor of Software Engineering Daily.
Wow!